Okay, so this is parameter estimation in logistic regression. I promised to write bigger from now on. And it's a joint work with Daniel Hsu from Columbia and myself. It was really a pleasure. I got to learn a lot from this collaboration. So I don't clearly remember how we started working on this. Maybe because I was working on something called one-bit compressed sensing, and it has some similarity. But here is a very standard problem that we looked at. It's called, so we had a data generation model. Okay, so bigger, right? Data generation model. And this is the logistic model. So we have tuples of xy, xn, yn. They are all from d plus 1. We assumed that xi's, they are all IIDs from this x, which is Gaussian 0 ID. And y is a binary random variable, takes two values, +1 and -1. And this happens, the +1 happens with probability 1/1 plus exponential minus x transpose some parameter theta, and -1 happens with probability 1/1 plus exponential x transpose theta. These two things sum to 1, if you just take. Okay, so this is the standard logistic regression problem. This is how my data is generated. It's not separable. And given such sample n samples, we would like to estimate theta, the parameter. Right? So theta is in r to the power d. So of course, this is a very well-studied problem. A lot is already known about this. So what are the things that are known? So in the limit of, so suppose d is fixed, d fixed, and n is increasing. Then it is known that the maximum likelihood estimator for this problem is pretty good. It's asymptotically normal. So what is the maximum likelihood estimator? Is that you just write this loss function for this type of probabilistic genetic model. We can write out explicitly the maximum likelihood estimator, which is the logistic loss. So what is the logistic loss? So let's say L theta equals to log of 1 plus exponential minus y x transpose theta. Okay, so this is the loss of this parameter with theta. So what we are doing in maximum likelihood is try to minimize over all theta 1/n sum I going from 1 to n log of 1 plus exponential minus yi xi transpose theta. Okay, so the arg mean of this, we call this theta MLE. So what I just said is that this theta MLE in this regime, it is asymptotically normal. What does that mean? This is theta MLE. So that in distribution, this is going to some Gaussian with mean the actual parameter vector theta. So maybe we give it a name because here the argument is theta. So let's give this a name theta star, right? This is a name theta star. So this is actually the true theta. So this is this, and it has a covariance matrix, which is the Fisher information matrix, right? So this is called the Fisher. I mean, if you don't know what this is, it's not very hard to derive. This is like a very generic result for all maximum likelihood estimators in this regime. What you basically do is you write out this loss function, and you want to take derivative of this loss and set it to 0. So what you do is you write out the loss function at theta star, take a Taylor expansion, the first derivative is 0, then you just take the subsequent term and neglect all others, you'll get back this something, and that is actually the Fisher information matrix over here, right? Fisher information. So this tells us something about how this parameter error, so parameter error is also a random variable with the same variance, except for that is zero mean. So by parameter error, I mean theta MLE minus theta star, right? So if this is my parameter error, that's also a Gaussian random variable, which is zero mean, and this is the covariance matrix. So from here, since theta is d-dimensional, you can sort of estimate that this variance, barring other constant term, which will depend on this logistic function, it is going to be something like the variance is proportional to d over n, right? So there is 1 over n coming here. This is actually an n sample, so sorry, this is going to be an inverse over here, I inverse. So n sample Fisher information matrix of the I, and the samples are IRD. That's why the variance is reduced by n and it's d-dimensional. So many of the problems are like this. So this has variance like so. This things so that means if we say that this is some sort of an error, so I'm basically saying that epsilon square is approximately, again, barring a lot of constants and other stuff, this is approximately d over n, or n, which is the sample complexity to have epsilon parameter error. So that is proportional to d over epsilon square. And this is very satisfactory for a lot of problem. You get to see this type of error rate. So n is about d over epsilon square if it is a high dimension. Okay, that's all very good. So by the way, there is a very interesting paper on logistic regression, exactly the same thing, and that so I said d fixed n goes to infinity, doesn't have to be, d can also go to infinity as long as, so there is a recent, like I think even in the 90s people knew that as long as n is greater than something like d log d, this is all going to go through, these are all fine, right? So there is a recent paper by Candice and Sar, I think 2018, 2019, perhaps it was in arXiv in 2018, I think it was published in 2019, something like that. And they showed that it is actually more nuanced than this. This maximum likelihood estimator may not always exist in the regime where n is proportional to d. So even if you have n to be 5d, which means you have enough number of samples, like 5 times as much as d, it is not necessary that maximum likelihood estimator exists. So they basically gave a diagram of when MLE exists or not. On one hand, you can have d over n. And on the other hand, you have something like the norm of the parameter vector theta and normalized properly. So they showed that something like this actually is over here MLE exist and unique, and here it doesn't. And it's a very decent result.
Actually, the curve hits the x-axis exactly at 1/2.
At 1/2?
And that is
okay.
Since the 60s.
Okay. 1/2 is after that.
Might just be confused, like why would the normalization for theta depend on n and not d?
It's interesting, but it's a digression. I don't. Okay, so no, I wanted to say that there are some answers in the paper, but I don't want to get into. It's like a completely different story. What should be the proper normalization to get something like this?
I guess what I mean is like the problem is like, you know, d is kind of intrinsic to the problem, and then you're taking more and more samples. So
right.
It's weird.
So this is some sort of like.
It doesn't matter, first of all, because here d is proportional to n. And second, in reality, I think if you take the normalization that the x is a unit covariance, as you say, then the normalization of theta as theta should be of order 1.
Yes, I actually want to come to how this thing plays a role, but let me hold on to that.
I was just going to say, because the cases where it doesn't exist or where the solutions are often infinity, but those are easy for other reasons.
Easy to do what? Yeah, maybe, yes. So you are saying that when there is, when MLE might not exist, but that doesn't mean that you cannot do predictions. So that's, yeah, I agree.
MLE doesn't exist means that it's set.
Yes. Yeah. Right. So, by the way, I don't want to spend too much time discussing this. This is interesting, but this is somewhat different from what I am going to say now, and I hope I have a lot to say. So, by the way, you agree to this, like in the classical regime, this asymptotic, this type of things are abundant, and we sort of agree to this type of scaling. What I want to say is, like, as we were also talking about this norm of theta, right? So what happens when norm of theta is really large? So I didn't really restrict theta over here. So what happens if norm of theta really large? Then this y becomes just the sine function. Right? Can you see? We can see that from here. So if norm of theta is really large, then when this x transpose theta star, so by the way, it's theta star. So x transpose theta star is very large. So when sine of x transpose theta is positive, this is a very large negative number in the exponent, so it is close to 0. So this is +1 with probability 1, right? So it's basically the sine function. Likewise, when it is negative, this thing is going to win out. So it just becomes the sine function. So this translates into a half-space learning problem somehow. And for this, we know exactly how the parameter varies, because we know that you need n equals to d over epsilon samples to get a parameter epsilon. Right? How do you know that? I think it's pretty easy to show. Actually, both the upper and lower bounds are easy to show and known since 50s or 60s. So you can, for example, think of, say, Gaussian hyperplanes. So if you are just taking Gaussian x, like Gaussian x's, like what I defined over there, then the like if you have 2 points, the probability that the x is going separating out these 2 points is actually proportional to the angle between those 2 points, which we call, say, alpha, divided by pi, right? So now what you can do is you can try to construct a covering of the, say, unit sphere. If you want to identify you see, you can only identify the direction. The norm information is completely lost. So when norm is large, norm information is lost, you can only find the direction. And the direction you want to estimate with epsilon error. And that you can do by doing these Gaussian measurements or such, because for any 2 points, the probability that it is going to be separating them is their angle divided by pi. And now you can construct a covering of the unit sphere, right, an epsilon covering, and then just use a union bound to show that if you have so many number of hyperplanes, there will be at least one that's going to separate any 2 points from the cover, right? So that will give you d over epsilon. On the other hand, you can show a simple lower bound as well, that this is, you need this many, because you see, when you have a d-dimensional space and you are cutting them with hyperplanes, so suppose you have n hyperplanes, so how many different parts they are being divided into, and then there are exact formulas for that. So I think that's going to be 2n choose d minus 1. And now you can construct a packing where any 2 points are at least distance epsilon apart. And then so all points on the packing has to be separated into this one of these partition parts, right? So you just do that thing and you will find n to be something like d minus 1 over epsilon, right? So this is tight. So what I'm saying, like, the bottom line is, for this case, we know exactly that this is d over epsilon. Whereas in classical statistics, we know that this is d over epsilon square. So something is going on with the norm of theta, and when it is small, it's something, and when it is big, it is something. So it's like, so we need to know n as a function of not only d and epsilon, but also the norm of theta. So in this talk, we are going to see that. So what if I want to write some n star, which is the sample complexity, as a function of d epsilon and the norm of theta star, right? So to make it well defined, let's do the following thing. Let me assume the parameter theta star is from the unit sphere, and I'm just going to separate out the norm and assume that the norm is known for now. Okay, so my model is changed slightly. Again, similar to before, x is n0 id, and y is plus minus 1, but it is plus 1 with probability 1 over 1 plus exponential minus beta, which is now playing the role of, and there is a reason we are calling it beta because, well, you know, so this is x transpose theta star, and with probability 1 over 1 plus exponential beta x transpose theta star, right? So beta is the inverse temperature. Right, so it's the inverse temperature parameter, and now we want n star, which is a function of d epsilon and beta. Okay. So what I'm going to do, I mean, the punchline is that we can exactly say what this is, and it is the following. So n star d epsilon beta. Tell me if you cannot read this part. So this, there are three distinct regimes. So in one case, this is indeed this. So this is the high noise regime, so to speak, or low. Yeah. So sorry. Yeah. So this is the high temperature regime. So in that case, what happens is it is d over beta square epsilon square. So in this case, my beta is less than 1. Beta is less than some constant. It is d over beta epsilon square, and beta is bigger than 1, but less than 1 over epsilon. And this is d over epsilon when beta is 1 over epsilon. So this is the main result. Okay, and you see that at corner points, like these actually match.
So this means it's these up to constants.
Yes, there are certain log 1 over epsilon factors as well, which shouldn't be there, but I think those are artifacts of our proofs. Barring those, I think this is exact scaling. Okay, so now for the rest, so this is the result. Now I think the rest is going to be a little, how we prove it is not super interesting, but a lot of things that we tried that didn't work. So I think what we tried but didn't work are quite informative. So I will try to go that way and like how we came about this result. So at the very beginning, of course, we didn't even know that this should be the correct scaling, right? So gradually we came to that. So what is the first thing that we should do? We should try to look at this logistic loss and try to analyze that, right? So that's a very well-known loss in machine learning, and then there are a whole literature on like excess logistic risk and so on. So we tried to do an ML theory, learning theory type analysis over here. So what does that mean? So we minimize this thing. Now I think I need to change this. Where is this? Yeah, so I need to change this slightly. I will have beta here, and I'm just doing minus beta over here. So this is the only change that I have to do. And theta MLE is the minimum of this. So I can try to see what is expected value of. So I want to write something like this: expected of L theta minus expected of L theta star. Right? So this has a nice form, right? And we will see why this is interesting. So if we can, and this expectation is with respect to data, so x, y, right? So if we can, if you can have a nice closed form relationship between here, then we can use some learning theory techniques, right? So So let's see what this quantity is. Let's first just find out expectation of L theta, right? So that, so this is equals to expectation over x, and so I'm first doing it for a fixed x, and then I will do it, take an integrate over x, right? So, okay, so this, so now y has this probability distribution right over here. Y has this probability distribution, so it is +1 with probability 1 over 1 plus exponential minus beta x transpose theta star. This is the probability that y is +1. So I'll just plug it in the logistic loss with y +1. So log 1 plus exponential minus beta x transpose theta, right? And the other term is just going to be 1 minus this thing. So 1 plus exp minus beta x transpose theta star. So sorry, this is going to be plus. And now this is going to be log 1 plus exponential beta x transpose
Arya,
theta. This, oh, okay.
but it's okay.
I think you sort. I will actually repeat this. So this, I think you will be able to see it if I do something like this. Is there? I don't know. I probably cannot move this thing. Okay, you can see it, right? So I will not write on the lower part of it. So now you see this is actually a pretty nice form, because now if I want to write out this thing, this is simply the expectation over x, the KL divergence of the Bernoulli 1 over 1 plus exponential minus b x transpose theta star and Bernoulli 1 over 1 plus exponential minus beta x transpose theta, right? And then there is a big bracket over here. Okay, so this is some KL divergence between two Bernoulli random variables. And we can actually calculate, yeah. Did I invert this thing? So no, I actually didn't write, because this theta star will come in the other term as well. So when I do the subtraction, it is, yeah, well, anyway. It will not matter, because what I want to do is, now I want to use some approximation for the KL divergence to connect this term to parameter error, right? And that's actually something that we will need till the end. So even if ultimately this approach failed, this is something that we needed. So so let's try to do that. So the way, like, okay, so it's a bit messy, but you can write KL divergence between, you know, this is something nice, because you can write KL divergence between two Bernoulli. Say what we have is something like G prime U. So this is actually the derivative of the logistic loss itself, right? So I'm just writing, so this is a generic thing, so you probably know this already, that you can write a Bregman divergence formula for KL divergence, which makes it much easier to handle. And it is actually in some very nice form, right? So if you have something like this, you can write this as, I believe, GV minus GU. Don't tell me this is the other way around. Minus G prime U V minus U. I think I wrote it correctly. If not, let's see. V U. I think this is correct. Anyway, so so now if you take expectation with respect to U, this is like not that difficult to handle. And ultimately what you get is that this thing, you can get a nice upper and lower bound on this term, right? So I believe the lower bound is going to be something like, so that is this term, right? I think this is the last line I'm writing here, and then I will move on to that part of the board. So expectation of L theta minus expectation of L theta star. So that is going to be upper bounded by something like beta square. Sorry. This is going to be upper bounded by beta square theta minus theta star square and minimum of half and beta. And this is actually lower bounded by beta theta minus theta star whole square. Okay. So what I can do now is I can try to actually upper bound this excess risk, and now I have connected this to this parameter error over here through a lower bound, right? So if I can have, so for that what I need to have something like a bound, or like bound, or like this is the standard calculation. So we'll try to do this right now. I don't need this data generation model anymore because this didn't work. Okay. So I have theta MLE, expectation of theta MLE, minus, let me just say that this L of theta equals to 1 over n, sum over I going from 1 to n, little l of xi, yi, theta, right? So that quantity over here, I can try to break it. So I am trying to calculate expectation of L theta star. So this can be broken down into expectation of L theta MLE minus theta MLE plus, since I have added something over here, I have subtracted something, I add that thing back, MLE. And then I have this term. So I will just do minus L theta star plus L theta star minus expectation of L theta. So you probably have seen this in kindergarten, I guess. Anyway, so you see what we want to say, that this term over here is net negative because theta MLE is minimizing this term. Right? So this is net negative. So I can just basically upper bound this. And when I take an expectation with respect to, say, for a better thing, this, like by this I'm saying that theta MLE is actually a random variable. So I'm taking this expectation, outer expectation again. So then expectation of this term is equal to this. So that's going to cancel out if I take that expectation. So I'm just saying this is expectation. This is going to be this, and in the bracket I will have expectation of L theta MLE minus L theta MLE. Okay, I can forget about this, so I will just write this to be upper bounded by, I can now take a supremum as usual. So I'll just take a supremum over all theta in SD minus 1. So actually this is the approach that I was discussing, which should be like the most standard thing that we could do. So this is going to be, so expectation over of L theta minus, this is going to be L theta, so, right? So we are looking at supremum of this, this empirical process over here. And then the standard things are you use this Rademacher complexity type thing. So first you do a symmetrization. So when you do symmetrization, you can just write this as expectation of L, and then you introduce a bunch of Rademacher random variable. Let me call them U. So then expectation over all those U's as well. So this supremum would then go. Sorry, the supremum will stay as a supremum that belong to SD minus 1. But this is just going to become 1 over n, sum over ui L theta, right? So this is actually L xi yi theta. So in the next step, what we can do, like since these are very standard, then I'm not really going to go over this too much. So this is the standard symmetrization. After symmetrization, you just use the property that this logistic loss is, there is contraction. So you use the Lipschitz property of this loss, and you write this to be something like, so it's beta constructive, so beta, and then x and theta sort of appear in this way, xi transpose theta, and you have some yi, something like this, right? But then what you have is, yeah, good. So, but then if you just do like after that, you have to just consider the fact that this ui, yi, xi transpose, so these are actually like, this is sum of Gaussian random variables, sum of n Gaussian random variables. So you can exactly calculate this thing out, and it will turn out to be something like beta times square root of d over n. Okay, so this thing ultimately is going to be, just looking at the time. I don't know how long do I have? 2:30 to, I have 20 minutes. Yeah. So this is going to be something like this. But this is bad. Why is this bad? Because I have square root d over n, and I have epsilon square here. So it's giving me a sample complexity dependence of 1 over epsilon to the power 4. Right? So this is not good. So that's why this, this Lipschitz type thing, that Lipschitz property of logistic loss, that's not sufficient to do this. So then there is a lot of literature in statistics on generalized linear model, asymptotic analysis of generalized linear model, and there is all this self-concordant analysis of logistic regression. So I thought, okay, maybe we can take an even closer look at logistic regression, and this is probably a very generic technique that is not fruitful, but those more closer techniques are going to be fruitful. So let me give you a brief overview of what this self-concordant type analysis of logistic regression is. That also didn't work, just a spoiler. But we solved some other problem learning that, so it's good. Yeah. And don't be afraid, I'm going to tell you what worked ultimately.
All right.
Yes.
Question. So these three regimes that you spelled out,
right?
That's the sample complexity for measuring a unit theta given. So you're not doing parameter estimation of beta. Beta is given to you. Fixed.
Beta is given to us and fixed. So there is actually a
This question of, so you guys are planning to work out the genesis?
So yes. So when beta is not given, there is actually a paper by Van de Geer and Kuchelmeister. I'll write out their names. Just last year, but they assume beta is unknown, but they don't take the logistic data generation model. They do a probit model for data generation and solve with logistic loss. So it's like a mismatched model. So I think, as far as I know, that's the only work where beta is unknown. Okay. But yes, that's the more general thing. So this, what I'm going to tell now, is actually a more this this optimization style analysis that actually that assumes the earlier data generation model where we didn't have beta separated out. So most of the literature there. So what actually they try to do is, we have the logistic loss that we are minimizing. Did I erase that loss? Okay. So no. So this loss function. So this is convex, right? Since this is convex, they try to use some some property like following. So suppose I have my theta star over here. If I can take epsilon radius, so forget about the constrained version. In the unconstrained version, if I take an epsilon radius wall around theta star and evaluate the gradient of this L function, right? So what I will do is I will take u to be a unit vector, and then I'm just going to take the inner product of epsilon u and the gradient of L theta. I'm not writing, so L theta is simply this function over here. Sorry, theta star plus epsilon u. And if I can show that this is greater than 0 for all u, then I know that there exists a stationary point of this L. That means derivative of L equals to 0, a stationary point theta such that theta star minus theta is less than equals to epsilon. Did I write it correctly? Yeah, if I show for all direction, sort of if you go towards that direction and you take the inner product with the gradient at this point that is greater than 0, and that happens in every direction, that means that within this there has to be some stationary point. Otherwise, this wouldn't have happened. And since this is a convex function, right, there is only one stationary point. It's nice in that way, and therefore theta MLE must be that point. So I get this kinetics, right? So this is the starting point of a lot of analysis in statistics. So once you have that, now what do you do for this part? So you have, so you want to show this, but this is hard to handle unless we do something nice. So what is the nice thing that we do? We write this as, okay, so this epsilon can be taken out. So as you can imagine, we write it as theta star plus epsilon u minus gradient of L theta star. Okay, now some term we have actually, so that has to be come back. So u and gradient of L theta star, right? So this, we want to show this to be infimum over all u. So there is a reason why we are dividing it into like this. I think when we take infimum over all, we separate out this infimum into these two terms. For this term, we take it outside over here, negative that. So what would happen is we just want to show that what would happen when we take infimum over this, that's just going to be the norm of this thing, right? So on the, so what we want to do is we want to control expected gradient of L theta star. That is something people can do, right? So they, like again, by doing these Gaussian integrations, they can try to handle this thing. For this part, you use, the reason I'm saying expected is because I will show that this happens with high probability ultimately. Right?
But the expectation will be 0 then. Yeah, theta star, because this is the gradient of the population.
So I will have something like this now, and then it will, right? So expectation will come outside of that. Yeah. For this part, well, it looks like we just have to use a Taylor series, right? But where do we truncate the Taylor series? That is the question. And logistic loss has some really nice property that people use. So eventually what we have to do is to go back to this function, right? This G prime U. So what was G prime U? G prime U, because this gradient, that's like, yeah, so that would involve computing this. So that's actually this function in disguise, and then there will be some xi transpose, right? So this is 1 over 1 plus exponential minus u. So if you do, so this is the function actually that we are taking Taylor series of, right? So if you do one derivative of this, you get, I'm just writing out like what you can do the calculation, it's pretty straightforward. This sec hyperbolic square u over 2. And if you do another one, then that's going to be twice sec hyperbolic u over 2, and this is sec hyperbolic u over 2 tan hyperbolic. So this is basically going to be sec hyperbolic square tan hyperbolic u over 2. There is a reason, and then there will be half. That half is going to cancel this thing. And since tan hyperbolic anything, this is actually between +1 and -1, we have this very nice property, and it was called self-concordant by Bach. I think this is self-concordant analysis of logistic regression. We had the property that absolute value of the triple derivative of this logistic loss is upper bounded by just the double derivative, right? So if you have that, then from here you can integrate back to have a nice approximation for the logistic for this quantity, and that's how you proceed. Like that's what you use in this this type of analysis, right? So we did spend quite some time trying to do this, but it turns out that this doesn't give us the scaling that we want, which was written somewhere. Did I erase it? It was over here. Oh, I just erased, right? Okay, anyway, I think that this I will not need anymore. Okay. So let me just write down that thing again, because I think so far I just said things that didn't work, and now I have only 8 minutes to tell you things that did work. Okay, so if you remember, n star d epsilon beta was d over beta square epsilon square, d over beta epsilon, and d over epsilon. Okay, so there are these three regime again, beta less than equal to 1, beta 1 over epsilon, and beta greater than 1 over epsilon. Okay, so far many things didn't work, but we did calculate that KL divergence, right? So we can use this for lower bounding, right? So at least we know that now if we have something like Fano's inequality, we already know if there are two candidate theta and theta star, we know what is the KL divergence between them. So we can use like a generalized version of Fano's inequality, and again construct like a covering, or a packing, and then just apply that to show lower bound for these two cases. This will just follow from the KL divergence expression that I had written at some point. Okay, so that will give me lower bounds for this, which exactly matches this two. Right, so I'm good with lower bound. And for this part, I told you that we can do, like, for the case of half spaces, we had this d over epsilon lower bound. So we can extend that argument. So Fano's, I had a nice Fano's argument, but that didn't pan out. Somehow we cannot make Fano work in this regime. But just that combinatorial argument where we were counting the number of parts this many hyperplanes do, and then constructing a packing, slight variation of that argument will give you lower bound for this. So we are all set with lower bounds, right? So at this point, we sort of gave up on the logistic loss, which is one good thing. So now we know that, okay, we didn't have to be married to, the maximum likelihood estimator. What about the other estimators? So it turns out that, okay, we gave up on that, but we didn't give up on this generalization style bounds that we had. So why don't we use 0, 1 loss? Well, there is no hope of doing it in polynomial time, but let's minimize 0, 1 loss because there is very strong generalization guarantees there, right? So what do I mean? So by 0, 1 loss, I'm not writing it down anymore, but there are the standard results that says that if your n is greater than this d over epsilon square log 1 over epsilon times optimum. This is the optimum 0, 1 loss. It doesn't matter what the data generation metric is, plus d over epsilon log 1 over epsilon. Then the prediction error, the excess prediction error or excess 0, 1 loss. So L01 of theta 0, 1 minus L01 of say theta star. This is upper bounded by epsilon, right? So this is some standard result again from I think 70s, 80s, 90s. People know this. So now previously we connected the excess logistic loss with KL divergence and therefore with parameter error. Now we just have to connect this with parameter error. So it turns out that we cannot connect. So this 0, 1 loss because of the logistics. So it's very easy to calculate what this thing is, but there is no nice connection with the parameter error that will give us this scaling. Okay, except for when beta is greater than 1 over epsilon. So if beta greater than 1 over epsilon, then we are in this low temperature regime. So the number of errors are so low, sort of the standard, this could have been even adversarial error, and even then this would work out, right? So in this regime, the 0, 1 loss actually works out and gives us nice guarantee on parameter error, and therefore we recover this one fully. So this is good. We are good with this. We have both upper and lower bound. We have for this two lower bounds, but no upper bound. Okay. So in 3 minutes, I will tell you what we did because I think I can actually erase all this stuff. So actually, when the number of errors is extremely high, then some other estimator works out. It's very noisy. The linear estimator, or it's called linear estimator by Plan and Varshnyin. And also, this is the average estimator by Sar. I think there is a. Yeah, anyway, let's stick to Plan and Varshnyin because we can just pick up. So what happens is, so you can take a theta, make a theta linear. So this estimator is arg minimizing some other thing. What is this thing? It is 1 over n sum over. So the linear estimator or the average estimator is just theta hat equals to 1 over n sum over I going from 1 to n yi xi transpose. This is also something that people have used for half spaces and stuff, right? So the linear estimate. So this we want this. However, we don't. We want this to be on the unit sphere, right? So we just normalize this so that you can write it as argmin 1 over n yi xi transpose theta belonging to S d minus 1, right? So it's just this thing. So now taking this as your loss function, if you just write that excess loss type thing, you will be able to connect it to parameter error. On the other hand, so for this you can calculate a generalization bound. So that's been done by Plan and Varshnyin for most part. We can just adapt their result to us. And this will give us our estimator because you can calculate the moments of this loss function easily. So whereas in the logistic loss function, the moments were a mess. We couldn't calculate them approximate them well. But for this loss function, you can do, because this is very nice, everything is good. So all is done. So we have upper and lower bound for this, but for this we just had We just had the lower bound. We do not have the upper bound. So ultimately, this worked out because of an observation that was made in this paper by Kuchel, Meister, and Van Dinkier, 2023. So they said that the logistic loss, so if you remember, so log of 1 plus exponential, in our terms, minus beta y x transpose theta, this can be divided into two parts. You can write this as log 1 plus exp minus beta absolute value of x transpose theta plus the indicator function of whether y x transpose theta is less than 0 or not, then x transpose theta. So this part is you can just verify, because when this term is indeed less than 0, that means this is actually positive, these two things are equal. When it is not, then this indicator is 1, therefore this is this value, which is log of exponential of this value, and therefore it can come inside of this log, and you will get back this term. Okay, let me see if I can. Okay, so now this loss has a name. This part can, this is the ReLU loss. Or hinge loss. Anyway. Yeah, there is because there is this is exactly the ReLU function, so but anyway, yeah, this is hinge loss as well. Just right.
Hinge is shifted, right?
Yeah,
so
it's
this is the
shifted.
perceptron loss. So
Yeah.
Perceptron means
Very different.
Yeah.
I mean, it's a shifted version.
Zero.
Yeah, hinge is, this doesn't guarantee any merge.
Right. Okay. Just in the interest of time, I will tell you this thing. So now this loss is if we take this loss, it is very easy to connect to parameter error. Why? Because this is just this logistic loss minus this bounded part, right? And you see in this bounded part, y doesn't appear, right? So what would happen is, if I take the expected value of the hinge loss evaluated at some theta minus expected value of the hinge loss evaluated at some other theta, right? So what would happen is, I will just get the excess logistic loss. And for this part, I will have something whose expectation is equal to 0, because the expectations are going to be same for theta and theta prime. So this part is this bounded part is going to cancel. So this ReLU loss is also very easy to connect to parameter loss, because this is just this logistic loss minus this term, which in expectation is going to be the same for all theta. It has no dependence on y. Good. So we can connect this to parameters. On the other hand, if we just worry about this part, exactly like this, the moments of this are not very hard to compute compared to, it's still pain, and we have to look at, this handbook of, mathematical physics, where they have all this integration with Gaussian measures done to compute the moments of this, but it is there. So we can just use this, use Bernstein inequality, and ultimately we get back this. So to summarize, now I've said whatever I had to say. For this, we use the linear estimator, which is polynomial time. Okay. For this, we use the 0-1 loss minimizer. This is not polynomial time, except for when beta is exactly infinity, when it becomes a half space, and we can use a linear program, or become separate. For this, we used ReLU loss, or just there, and used similar argument. However, it's constrained because my theta is in SD minus 1, right? So I have to. So this is a constraint minimization problem. Although this is convex, this is on the sphere. So we don't yet know the computational complexity of this. It might be the case that we can still it's nicer because it's on the sphere. So all this Riemannian gradient descent or something maybe. So we have not looked closely into that. Yes.
we had the result that was actually minimizing the leaky value of the sphere.
It's the? Sorry.
We had, well, I guess, we had the result that it was minimizing the leaky value of the sphere, and you can do that efficiently. And
you can do that efficiently.
It's going to be close to a value, so I think.
I see. So you were saying that the minimization of ReLU loss with the constant being on the sphere can be solved. Yeah, I think that.
I think so. Yeah, because if you take just a leaky value that's close to I think actually the argument should probably work out.
Okay. Yeah, so we also hope that this will work out, except for this 0-1 loss part. I think it should be, and the linear part, this is actually, yeah. So if this works out, and somehow we can make this, do something with this, perhaps we can show that there is no computational statistical gap. But as of now, we didn't check that. Okay, so that's all. I didn't know. I think I went a couple of minutes over there.